Here we are with our first buoyancy problem. So for these buoyancy problems are really just Newton's second law of force analysis problems. Hopefully you're seeing that. The only new content at all in the buoyancy problems is something called the buoyant force. So the buoyant force is a new type of force, right? It's a contact force. Spend some time just kind of wrapping your head around buoyant force. But what I want to draw your attention to right now is Archimedes Principle. So a lot of times when students see and learn and think about Archimedes Principle, they conceptualize it as being like a much bigger concept than it really is. So I just want to remind you that all Archimedes Principle tells us is that the buoyant force, the magnitude of the buoyant force, there's no hat on that, right, is equal to the weight of the displaced fluid. That's it. That's what Archimedes' principle tells us, that the magnitude of the buoyant force is equal to the weight of the displaced fluid. And these are just magnitudes. So buoyant force is always going to be, the direction of buoyant force is going to be direction up, and weight is always going to be direction down, right? So these two are never going to have the same direction. Um, Buoyant force being like radially outward from the center of the planet, if you want to look at it that way, and weight being always radially inward toward the center of the planet. Now, the reason we have buoyant force, and again, I want you to spend time on this, but the reason we have buoyant force is that there is a gravitational force, right? Buoyant force is dependent on gravitational force because of gravitational force. Basically, what you have is you have this kind of increased pressure as you move down in a fluid, and that is basically the genesis of the buoyant force. So it really is worth it to spend time with both the textbook and lecture videos when it comes to that topic, just so that you have a pretty clear understanding of what buoyant force is. But when it comes to applying it, and then we talk about applying Archimedes' principle, again, remember that all Archimedes' principle does for you is it gives you the magnitude, or a way to calculate the magnitude of the buoyant force. Everything else you do with these buoyancy problems is stuff you've done before. Everything else you do. All right, so let's talk about this problem. This will hopefully make a little more sense when we apply here. Rectangular air mattress has dimensions A, B, and C and some mass M. Sure. What additional mass can it support in water? So in this case, we're looking at like I don't know. So we have some water, okay, and we have an air mattress. And what we're going to say is that this air mattress maximally, right? It's asking here what additional mass, I should say here, maximum can it support in water. So we can say that in order to get the maximum out of this air mattress, we can submerge it all the way. So let's say it can be all the way submerged there in order to max that out. So this is your air mattress, and that we're pushing beneath the water. And I'll call this, so this is the mattress itself, and we're given the mass of this is little m. And now let's say what this question is asking us about is what load can we put on here? So let's say here's the load that we're putting on the air mattress, and I'm going to let that be mass big M. Great. And the question is really asking us just for big M, right? Like what maximum amount, and here, let me add this here. What maximum amount can I put on there? All right, good. And this could be a relevant question, right? If you're actually looking to build something or move something, you will need to know, like, what is the maximum I can do here, and then work from there. So what do? Well, we draw a free body diagram. So in this case, what I'm going to do is I'm going to draw a free body diagram of the mattress and the load as a system. I don't need them to come apart. Nobody's asking me for any information about the internal forces, that is the forces between them. So I'm just going to look at them as a system. So I'll draw a free body diagram of the mattress and the load I have on top of there together. So what does that look like? Well, if I look at them as a system, I have the weight of both of those, right? So M plus M, G there. And then upward I have buoyant force. And again, just as always, right? You say you get your one invisible force, which is weight. We've got that. Apart from that, you need contact forces. So if I'm looking at these two bodies as a system, the internal force of the normal force at their point of contact, where they're in contact with each other, that's an internal force. So it doesn't show up on our free body diagram. What is in contact with the system is the fluid, though, right? The air mattress is in the water, and the water is exerting a buoyant force upward. So that's why that ends up on the free body diagram. And this is a phenomenon you're all really familiar with, right? Something floating in the water. So that floating in the water means the water is supporting it in some way. We don't classify that as a normal force, though, right? When a fluid is supporting or a fluid is exerting an upward force on a body, we don't classify that as a normal force. So watch out for that. Normal forces are exerted by surfaces. So when you have a fluid and the pressure differential in the fluid is causing this upward buoyant force, we need to name it as such, as a buoyant force. All right, so I'm going to go ahead and say upward. And here I'm wanting that maximum buoyant force. Obviously, if you put a smaller load, the mattress could still support that, but this question is really asking us for a maximum of everything, right? All right, so now I'll just apply Newton's second law. So buoyant force here minus the weight of each of those is going to be equal to their masses times acceleration. This is a really nice little scenario. These are just floating there. So they're in equilibrium. There's no downward acceleration. There's no sinking. We're just wanting to support this as like a floating object. So that is equal to 0. In order to max, then we're going to assume the whole mattress is submerged, is under the water. So now what we're going to do is, so if when you're doing a buoyancy problem, you'll draw your free body diagram. Buoyant force will be somewhere on the free body diagram. You'll do your Newton's second law as usual. So here I have buoyant force is then, I could say, equal to M plus M G, right? But to solve this problem, like we're trying to solve for big M, and now we have two unknowns in this equation. Buoyant force is unknown and big M is unknown, right? So this equation isn't enough. This is where I now need to go over to Archimedes' principle, and I need to solve for the magnitude of buoyant force using Archimedes' principle, which tells me buoyant force is equal to the weight of the fluid I have displaced. So I'm going to use that. And for this case, I can say buoyant force is equal to the weight of the water that the mattress displaces. Well, what's that going to be equal to? Well, that's going to be equal to the mass of the water that it displaces. So the mass of the water is just going to be the density of the water multiplied by the volume of the water. The volume in this case is ABC. The mattress displaces its own volume in water. And then to make this, of course, a weight, this is a mass, so to make it a weight, I need to multiply by gravitational acceleration there. So that gives me the magnitude of buoyant force. So that right there was me using Archimedes' principle, right? So this is, how did I figure out this? By Archimedes' principle. Great. Now I can take this expression and I can bring it back over here, right? And solve for what I need to solve for. So on the left-hand side there, I can substitute for buoyant force the weight of the displaced fluid, ABCG, is equal to mg plus big mg. All right, now you can see that we're getting somewhere and that you have one unknown, that's big M, and you're going to be able to solve for that. So big M will get rho of water times the volume of the air mattress minus the mass of the air mattress. And that's our final answer there for what is the additional load you can place on top. So most of this hopefully felt really familiar with these buoyancy problems. It helps us stay organized, and like with any kind of force analysis problem, have a physical diagram, have a clear free body diagram and remember that the new content for these problems is simply a new force called buoyant force, and we use Archimedes' principle only to help us calculate the magnitude of that buoyant force.